Now the question is, should this dynamic panel bias be upward or downward? Should OLS estimates of dynamic panel data model be a case of overestimation or underestimation? To understand this, let us assume a firm experienced a negative employment shock in 1980, a negative employment shock, right. So, if that is the case, what will happen in 1981? In 1981, if this is a negative employment shock, in 1981, your YIT minus 1 will be lower, your AI will also be lower than what you observed in 1980. There is a negative employment shock. So, throughout that study period, this negative impact of this negative shock will be there. So, that means what will happen? What is AI basically? AI is the unexplained employment effect which you cannot explain, which is unobserved. Unexplained employment effect will be lower than the sample average because of the result, as a result of this negative employment shock. So, if you consider only one period, there is a shock in 1980, negative employment shock. As a result of which, when I go to next period, the model will try to adjust. How it will adjust? YIT minus 1 will be lower and this AI will also be lower. That is how lower than the previous period. That is how it will slowly adjust. So, since YIT minus 1 is lower, AI is also lower. So, that means there is a pattern, a similar pattern that we observe in YIT minus 1 and the unobserved effect AI, and as a result of which correlation between YIT minus 1 and AI is actually positive, a positive correlation between AI and YIT minus 1. And because of this positive correlation, OLS estimates is biased upward. So, this positive correlation basically leads to OLS estimates to be biased upward. Okay, OLS estimates to be biased upward, and that is what, that means this value what I am getting 1.04 is actually a biased estimate which is biased upward. We can easily check that it is not less than 1 for dynamic stability. So, we can understand this is biased upward. Now, what will happen if we apply fixed effect transformation? Okay, fixed effect transformation will always also lead to biased and inconsistent estimate, we have already proved. But the question is, will these fixed effect estimates be biased upward or downward? That we need to understand. So, to understand that, we will once again derive the fixed effect transformation. So, FE transformation is basically YIT minus YI bar equals to rho YI T minus 1 minus YI dot minus 1 bar. And what is this? We basically say this is the mean of this value. plus ai will get cancelled out, and then you will have VIT plus minus VI bar. And we said this VI bar contains VIT minus 1, and that is again correlated with YIT minus 1, but this negative sign before VI bar means the nature of the correlation is negative. So, what I am saying, VI bar contains VI t minus 1, and that is the reason there is a correlation between yi t minus 1 and Vi bar, or sorry, we can write Vi t minus 1, and that means we can say that actually this entire variable yi t minus 1 is actually correlated with this transform error term, which is Vi minus Vi bar. So, this results in yi t minus 1 is correlated. So, this is correlated with the Vi t minus 1. So, that means we can say that this is correlated with this, and since there is a negative sign, the negative sign before Vi bar indicates that this correlation is actually negative. Okay, this is negative. All right, because of this negative correlation, FE estimates are biased downward. So, this is also dynamic panel bias, only thing is that this is biased downward, unlike the OLS estimates which were biased upward. Okay? That is the reason. So, what you will do? We can do couple of things over here to understand the consequences. See, when we have this type of unobserved effect present in the model, before estimating the direct fixed effect transformation, what we can do? So, this is basically we are trying to purge, this is basically purging the fixed effect or AI or unobserved effect. Okay. How will you do that? Solution 1. Solution 1. What you can do? We can actually bring out AI from the error term by including individual specific dummy, right. So, what we are doing here, all these problems are arising because this fellow yi t minus 1 is getting correlated with AI, and that is leading to some kind of dynamic panel bias, if we apply OLS, we saw already that it is upward. Even when we are trying to transform this fixed effect, then also there is some kind of bias, but it is downward. So, what we are trying to do over here, we are trying to understand that when you have AI in the model, there are couple of ways by which you can actually get rid of this unobserved effect. One is, the solution number 1 is, you bring out AI from the error term. How do you do? You consider that individuals are different, and how do you model your the situation? You simply include individual specific dummies in your model, and then actually that will lead to LSDV situation. Least square dummy variable, we all know from our basic from our earlier discussion on panel data that older version of the fixed effect model is basically LSDV. What does LSDV do? LSDV basically brings out the AI component from the error term by including individual specific dummies in the model. Why you are doing this? Because sum of my explanatory variable yi minus 1 was correlated with the error term, basically with the AI. So, if you do that, then you will get the LSDV model. And how do you estimate that LSDV model? Again, what we can do? We can regress your dependent variable is n, and then you have so many in L1 and then again in L2, and then you will have W. Where is your W? Is wedge is this is W. This is W, and then WL1. Then you have capital, then lag of capital, then second lag of capital, and you have output YS, then first lag of output, second lag of output, and then you have ER dummies, and then you need to include individual specific dummy, which is I dot ID. If you remember, I dot ID command, if we put in Stata, that will include individual specific dummies in the model, and we will get least square dummy variable model. So, this is my model. So, if you do that, then look at what is happening. What is the variable? 0.73. So, that means the coefficient of the lagged employment is now 0.73. So, which is just the opposite of the previous case. In the context of OLS, it was biased upward. In the context of FE transformation, my estimates are biased downward. Why it is downward? Because as I explained, YIT minus 1 is correlated with VIT minus 1, which is there in VI bar, and since there is a negative sign over there before VI bar, this correlation is negative, and this negative correlation is leading to a situation where estimates are biased downward. Okay. So, what we have learned over here? We have learned two things. First of all, how to bring that AI component out from your error term to estimate an older version of the fixed effect model, which is least square dummy variable model, by putting I dot ID command. And if we do so, then we will get the coefficient which is less than 1, definitely at least dynamic stability is maintained, but it is biased downward, right. Now, there is another way. What we can do? Another way of estimating this is basically we can we can directly put xtreg command, xtreg, and then again your n, then nl1, then nl2, then w, then wl1, lag of wedge which is wl1, and then you have capital, then first lag and second lag of capital, then you have ys, industrial output, first and second lag of that, and then you have ER dummy, and you have to put FE. So, instead of regress, this is the same standard fixed effect transformation, fixed effect model. So, basically what we are doing, we are, if you do so, then again similar estimate, look at 0.73294. So, this is the newer version of the fixed effect model. LSDV is basically older version of the fixed effect model. So, what we have to observe over here, look at the F test, which is basically 1.89 and highly significant. And what is F test? If you recall, in the context of fixed effect model, we discussed this. F test basically says whether the unobserved effects are significant or not. So, that means combinedly status UI is basically the AI what I am denoting over here. So, A1 equals to A2 equals to A3 dot 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 this AN, they are combinedly significant or not. So, joint test for this, joint significance test for this unobserved effect given by this F test, and that is also highly significant, indicating the presence of significant unobserved heterogeneity in the model. So, this is second way of bringing out the AI component from the error term, because that is actually creating the problem. Okay, that is actually creating the problem over here, because my YIT minus 1 was correlated with this, right. Now, both the models shows my estimates are actually biased downward, right. There is another way, another solution is, third solution is that removing solution 2 is, so this is solution 1 LSDB, solution 2 is basically fixed effect transformation. And solution 3 what we can do, we can remove form specific unobserved effect or AI from all the variables, and then run the regression, run the final regression on the residuals. Okay, residuals, all right. So, if we do so, that is basically a mean deviation transformation I am talking about. Mean deviation transformation. Okay, that means YIT minus YI bar kind of model. Why we are doing this? Because if we do so, AI will get eliminated, because AI does not change over time and mean of AI is actually AI. So, AI will get eliminated. This is another way. And how do you estimate this type of model? What we have to do? We have to use data's XTData command. So, this is XTData, then again in, then in L1, sorry, in L1, then in L2, in L2, then W, and then WL1, and W, and then after that we have capital, first leg of capital, second leg of capital, and we have output, then first leg of output, second leg of output, and then we have var, YR star, and then we will put FE. So, by putting this command, what I am doing actually, I am removing the AI component from all the explanatory variable. I am removing from specific unobserved effect from all the variables, and then I will be using the residuals of all those variables in my final regression. So, it is nothing but XIT minus XI bar. Okay, right. So, XIT minus that unobserved effect. So, I am removing all this from my explanatory variable. This is we are doing as XTData command, and then I will be using regress in, and again in L1, in L2, and then W, and then WL1, then I have capital, then capital 1, capital 2, then YS, YS1, YS2, and then I have ER dummy. So, look at this, same coefficient 7.7329, here also it was 0.7329, and then here also it is 0.7329, right. So, that means what we have proved today, that when we use OLS and fixed effect transformation in a dynamic panel data model, that gives rise to a dynamic panel bias. Why it is happening? Because in the OLS model, we are ignoring the fact that YIT minus 1 is actually correlated with AI, and that positive correlation is leading to upward bias. In fixed effect transformation, what is happening? YIT minus 1 is correlated with minus that VI bar, because VI bar contains VIT minus 1, which is actually correlated with YIT minus 1, and a negative sign before VI bar is actually leading to underestimation of the fixed effect transformation. So, one thing we have learned here, we can write that fixed effect estimates are biased downward. So, what we observe that you have OLS here, you have FE over here. FE you can get by 3 alternative ways. either by estimating LSDV or by estimating direct FE or by removing the firm specific effect from all these explanatory variable and then running this model. So, this is upward biased. This is downward bias. So, that means the true estimates should be actually between, since it is upward, it should be less than this, but it should be greater than this. Okay. So, true estimates then must lie between OLS and FE estimates. So, OLS gives upper bound, FE estimates gives downward or lower bound of the estimates in a dynamic panel data model, and we can always check whether my true estimates are actually lying between OLS and this or not. So, this is a very good post estimation checkup. Whatever dynamic panel data model we estimate, after estimation we can very well check whether the estimates are lying between OLS and FE. If it is lying, then only we can say that at least theoretically my estimates are satisfying the upper and lower bound. Okay, that is what I am talking about. Okay. So, when neither FE nor OLS can't be applied in the context of dynamic panel data model, then what is the solution? Solution is, if you recall, we need to go for Anderson and Hesiod's approach. And once again, what is Anderson and Hesiod's approach? Anderson and Hesiod. So, he suggested first you take the first difference of the model. So, yi t minus yi t minus 1 equals to yi t minus 1 minus yi t minus 2 plus beta xi t minus xi t minus 1 plus vi t minus vi t minus 1. So, since yi t minus 1 is correlated with vi t minus 1, we need to use IV, that is what Anderson and Hesiod suggested, and IV can be of two types. So, what should be the IV? First one is delta yi t minus 2 or yi t minus 2. Now, advantage of using yi t minus 2 is that it will give you enough sample length, because if you take yi t minus 2, that observation would be available only from t equals to 4, but when we are taking yi t minus 2, then it is available from t equals to 3. If you go back and see our instrument matrix, the first observation is available from the third period yi1. Okay. Anderson and Hesiod's approach, that Z matrix, if you recall, that first observation is lost, and then this is yi1, then dot 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 yi t minus 2. So, this is for t equals to 3. But if you take delta yi t minus 2, that means my first observation would be available only from t equals to 4. So, at least one more period of observation we can have if we use the second order lag of the untransformed or level variable yit minus 2. And when your sample size is small, then one extra period also matters in the efficiency of your estimates. So, that is why we will be estimating our first dynamic panel data model using Anderson and Hesiod's approach by taking yit minus 2 as instrument for yit minus 1 minus yit minus 2. Okay? That is the first approach. We will estimate and we will see, following Anderson and Hesiod's approach, whether my estimates are lying between OLS and FE. If it lies between this interval, at least the first criteria is satisfied, that my estimates, my dynamic panel data model estimates are lying within the theoretically defined upper and lower bound. If it doesn't, then we cannot use those estimates, because first of all they are not lying within the theoretically defined bound. It must lie between the two. So, we will be using this Anderson and Hesiod's approach, the first model of dynamic panel data model, in our next class, and we will check whether that is satisfying the upper and lower bound or not. With this, we are closing our discussion today. In our next class, once again we will be using the same data set and we will try to estimate this Anderson and Hesiod's approach. Basically, instrumenting yit minus 2 for yit minus 1 minus yit minus 2. Okay? That is what we will do. We will not be using delta yit minus 2 to start with, because as I said, that is available only when t equals to 4. This is available from t equals to 3. One extra period also matters. Okay. With this, we are closing our discussion today. Thank you.